All right, good evening and welcome to our final class meeting for MT225 for the spring 2021 semester. The Today's our last official class, and I don't have any new content that we're going over prior to our final exam on Wednesday evening. Wednesday evening at the hangar. Let's make it about 5:10 or so because it's a little bit of an extra delay to go and get the pizza and get back with the bridge on Floyd Ave out. But we'll get that picked up and we'll have some sustenance to sustain us through the final. Now it is a long exam. It's if you look at the one that's posted online, this is May 17's final exam, so it's got a few years on it. But this one was usually my finals are 9 to 10 questions, and it's budgeted basically for a 2 to 3 hours. It's a comprehensive final exam, so it's going to cover pretty much everything from the beginning. And so we'll take a look here. You are allowed 4 index cards, 4 4-inch by 6-inch index cards, so you can put anything you want on that. And I do have the paper copies from the people who took the exam in person, and I'll try to remember to hand those back tomorrow. It was a little bit of a hectic day today, but I'll try to remember to catch people at the hangar to hand those back so you can get your index cards back. Let's see here. So let's start with problem 1. Now tonight, I'm not going to work out everything in detail unless one of the people online wants me to. For the most part, I'm just going to kind of go through the setups. The full solutions are online, so you can check that out. So here, problem 1 is kind of a basic math problem. We started off the class way back when, 16 weeks ago or so, it was closer to 14 weeks or so ago, with basic math and things like unit conversions, solving equations, and so on. And in our first problem, it says that let me zoom in a little bit here. Yep, there it is, page width. There we go. So we have unit conversion problem up first, where a particular aircraft's maintenance manual is stating the required torque for a special fitting is 2,422 inch kips, which is a really special torque. The available torque wrench is calibrated in foot-pounds, so we need to convert from inch kips to foot-pounds. So you got to find out what torque setting to use. And to do that, we've got 2,422 inch kips, and we want to go to foot-pounds. So we've got to convert the inches to feet and the kips to pounds. And this is basically an application of the box method, where you plug in your conversion factors. 1 foot is 12 inches, and the relatively simple 1 kip is 1,000 pounds. And you can use that to figure out what the torque is going to be. So since we've got inches in the top, we'd have to divide the inches out. So we'd have 1 foot to 12 inches. We've got kips in the top, so we've got to put the kip side here in the bottom. That would be 1 kip. And that would put 1,000 pounds here. If we've got it set up right, the units we want to get rid of will go away, and the units we want will appear, foot-pounds. So we're going to multiply 2422 by 1,000 and divide it by 12, and that'll give us our answer in foot-pounds. And I'll leave the calculation to the solutions, but that's the setup for it. So next problem, we had to solve the following equation for x. So this is a solve the equation, hopefully something pretty straightforward after all the algebra we did. You'd get all the x's on one side, all the numbers on the other. If you subtract 6x from both sides, you'd have 3x on the left. Subtract 2 from both sides, you'd have negative 12 on the right. And 3x equals negative 12, so x must equal -4. And you could check that, plug it back in, and make sure it works. Here we've got our simultaneous equations. That bears a little bit more examination, since we didn't have to do too much of simultaneous equation work. But here we have 2x minus y equals 3, and 4x plus 3y equals 11. Now, the key to simultaneous equations is to eliminate one of the variables, to find some way to combine the equations so that one of the variables is eliminated and you end up with one equation in one unknown. Well, the keys I gave you when we looked at this were to think about variables that had sign differences built in already, like y here is negative in one equation and positive in the other. That will cancel out if we can get the coefficients to match. Well, in the bottom equation here, we've got 3 in front of the y. If we can make a 3 in front of the y in the top equation, we could add the two together and cancel out the y's. And we can change the equations any way we want as long as we don't upset the balance. If we multiply the top equation by 3, that means to multiply every term by 3, we'll get an equation that looks different but really says the same thing. Here we'd have 6x minus 3y equals 9. Same equation, just each term is multiplied by 3. Well, if we bring over our original equation, 4x plus 3y equals 11, if we add these two together, we have 6x plus 4x, that's 10x. Negative 3y plus 3y is 0y, so that goes away. And 9 plus 11 is 20. Divide both sides by 10, and x equals 2. Now, don't stop there. Big mistake I've seen people make with these equations and on these exams is they stop when they get x equals 2. That's only half the solution. You've got to go back to either one of your original equations and plug in x equals 2 so you can solve for y. And the top equation looks simpler, so I'm going to use that one. I'd take 2 times 2 minus y equals 3. So that's 4 minus y equals 3. Well, you might even be able to solve that by inspection at this point. Something minus y is 3. That something's probably 1. You could work through the algebra, but y is going to come out to be 1. So my solution to a set of simultaneous equations is always two numbers. In this case, x equals 2 and y equals 1. And that's the math problem. Then we went on to a little bit more math here. Next big topic that we covered was trigonometry and how to use sine, cosine, and tangent. So you've got a triangle problem. Here we want to find the unknown angle and the unknown sides in that triangle. Well, and it says there's an added wrinkle there to report your answers to 3 significant figures. So we have, if we look at the triangle we've got a 63-degree angle in the lower right-hand corner, and we've got the opposite side, which is 10. We're missing the hypotenuse, and we're missing the adjacent side. So we're missing the hypotenuse, and we're missing the adjacent side. Well, to kind of brute force it here, we can put our definitions down. Sine of an angle is the opposite over the hypotenuse. Cosine of an angle is the adjacent over the hypotenuse. And the tangent of an angle is the opposite over the adjacent. And we want to find out which of these three will work. We can take care of the first piece of the problem by figuring out the complementary angle here. They asked us to find the angle and the missing sides. So to get to 90 from 63 is 27. To meet the 3 sig figs requirement, we need to write it as 27.0 degrees. But maybe I made a mistake doing that. and I'm not too sure. I could have messed something up. So I'm going to use the 63 since that was given to me. So we're going to use 63 for our angle. I've got the opposite side, so I know the opposite side. I don't know the hypotenuse or the adjacent. That means I can't really use cosine. So I can take the sine of 63, and that'll be 10 over the hypotenuse. And then I've got the tangent of 63 is 10 over the adjacent. And then it's just a simple algebra problem from that point, cross multiply and solve. So if you flip these around, you'd get hypotenuse is 10 divided by the sine of 63, and the adjacent is 10 divided by the tangent of 63. You get whatever your numbers are, round them off to 3 sig figs, and you've got your answers. So that would satisfy that problem. Now, the advantage of having as many problems as we do on the exam is that it means each problem's somewhere in the neighborhood of about 10 points. So you don't necessarily have to be able to do well. You don't necessarily have to be able to get every single problem 100% right. You can one problem alone isn't going to hurt you. So if you run into a single problem you have trouble with, get as much partial credit as you can and come back to it. Or if you can't figure it out, and abandon it, and it's probably not going to hurt too much. It's not like it's 30 points or 40 points. It's 10 to 15. Let's take a look at problem 3. Problem 3 is our first equilibrium problem on the exam. And here is a Cessna 172N model at max takeoff weight, which is 2,200 pounds without the max gross weight STC. It's being held off the ground by a hoist. Hoist is attached at the nose and the tail as shown. The strap connecting the hoist to the tail carries a load of 1,650 pounds and is at an angle of 30 degrees to horizontal. And they want us to find the unknown tension and the unknown angle and state our answers to 3 sig figs. So if we look at the situation here, we've got a single lifting point with 2 straps. So we've got a concurrent force problem. All the forces interact at that one point. So if we draw the free body diagram of that one connection point, we'll figure out our forces. Don't try to use any of the numbers down here. They're just labels. C-172N is the make and model of the aircraft. N733 Mike Lima happens to be my tail number. So that's in there. Don't use those. They're not things to calculate. So let's draw the free body diagram, get the problem set up. So we have 2,200 pounds. So here's our connection point. We've got 2,200 pounds pulling up. Down here at 30 degrees to horizontal, we had 1,650, I believe. 1,650 pounds. And then they want us to find some unknown tension at some unknown angle to horizontal. So that's our free body diagram. Now, first, we can at least believe this is in equilibrium. It looks like it should be able to be in equilibrium. The forces all seem to have good directions to them. And with rope or straps, you only have one direction. So it's not too hard to figure out. We'll draw a coordinate system. And these might be a lot easier to look at now, by the way, after you've all been through truss analysis and method of joints and all of that. This was basically the fundamental problem in method of joints, was to figure out your equilibrium of a concurrent force problem. So here we've got our coordinate system, and we can break up the vectors and do our sum of forces in the x direction and our sum of forces in the y direction. Well, in the x direction, we're not going to pick up anything from the 2,200 pound force. We're going to get a negative value for our 1,650. We're going to get the adjacent side. So it's going to be 1650 cosine of 30 degrees, and that's to the left, so it's negative. And then we get to our unknown. And this is where you can make or break the problem. If you try to do t cosine theta and t sine theta, you're probably going to end up with a set of equations that's going to be hard to solve. Instead, whenever you don't know anything about the force, magnitude or direction, break it up to components instead. Call it Tx and Ty. Then at least we'll get numbers for the components, and then we can build the triangle, find the hypotenuse, and find the angle. So here we've got a positive Tx, and that sum will have to equal 0. In the y direction, we've got a positive 2,200 pounds. We've got a negative 1650 sine, the opposite side, sine of 30. And then we've got minus Ty. And that'll equal 0. Now, the good news is both of those equations can be solved pretty easily. T cosine 1650 cosine of 30. And they wanted 3 sig figs, so I'm going to keep 5 in my intermediate terms. So this will be negative 1428.9 plus Tx equals 0. And here we've got 2,200 pounds minus 1650 sine of 30. That's 825. Oops. Minus Ty equals 0. So that'll give us 1375 minus Ty equals 0. So pretty quick to solve for Tx and Ty. Add 1428.9 to both sides here, and Tx is 1428.9 pounds. So that's how much is pulling to the right. Ty, if we work through the algebra on it, and make sure you can do this to get your signs right, Ty is 1375 pounds. That's 0.0 technically, although I didn't have to do any rounding for that one. Now that's not the end of the problem. The problem specified tension and angle. So we have to build that. We can pick up this Ty vector and move it over here. So we've got Tx is 1429 or 28.9 pounds. Ty was 1375. So from that, Pythagorean theorem will tell us the magnitude. So T is going to be the square root of 1428.9 squared plus 1375 squared. The angle, inverse tangent of opposite over adjacent. And make sure you're specifying the angle that they're asking for. Don't go to vertical if they are asking for horizontal and vice versa. So opposite over adjacent. The angle will be the inverse tangent of 1375 over 1428.9. And whatever that works out to be. That's the basic setup on that problem. Go on to the next one. If you think about what we did next, we got into beam problems. We got onto loads on beams, non-concurrent force problems, and finding the reactions. And that just so happens to be the, not quite the next one. I got a little problem in here that is possibly similar to something we've seen on a previous homework assignment. But here we've got a landing gear illustrated. One of the big things we had to learn about to be able to handle non-concurrent force problems, we had to be able to handle moments. And there's a picture here of a landing gear. I'll scroll down to it here in a second. But they ask here, or I should say I wrote these, find the moment due to each of the forces about the trunnion A, and be sure to state your sign convention, which moments are positive and which moments are negative. Well, here's this landing gear. We've got 3 forces on it. We've got 100 pounds pulling on the wheel, and that's 4 feet away from the pivot point. We've got 150 pounds on this drag brace, and that's 2 feet away from the pivot point, but it's at an angle. Then we've got this 200 pounds, 1 foot away, also at a pivot point. Now, the 200-pound force is going to make a clockwise moment. So will the 150-pound force. That'll make a clockwise moment. 100-pound force is going to make a counterclockwise moment. And we learned counterclockwise moments are positive and clockwise moments are negative, although you could pretty much get away with whatever you want in this problem as long as you stated it. But our traditional statements would be clockwise negative and counterclockwise positive. So the real trick to this problem, there's really not an equilibrium to solve or anything like that. All this problem is and it's not really worth a whole lot of points. I think this one's worth like 5 or 7 points, something like that. It's just to see if you can calculate moments in different situations. So that's pretty much it. So let me sketch it down here. We've got, and I'm going to make a much more simplified drawing than what's in the than what's in the picture. We've got 100 pounds down there at the bottom, pivot point A, that's 4 feet away. We've got at halfway, we've got this 150-pound force at 30 degrees to horizontal. And then at 1 foot away, we've got this 200-pound force. And be careful of the angles here. The angle there is 75 degrees to vertical. So you got to be careful about how the angles are detailed. Here we've got 30 degrees. Actually, no, excuse me, I'm wrong on that. 30 degrees is also to vertical, not horizontal. So let's get that drawn right on here. All right, so we've got an angle of 30 degrees here, and I think I actually specify that. The drag brace is at an angle of 30 degrees, and the gear is the hydraulic actuator is at an angle of 75. So let's see what the simplified drawing looks like. That's basically my simplified drawing there. 100 pounds of force 4 feet away from the pivot point. This is 2 feet and 1 foot, so all relative to that point there. So those are our arms. The critical thing to remember to figure out this problem is that moment is the perpendicular force times the arm. So let's take the moment due to the 100-pound force here. The arm, the distance from the pivot point to the point of application, and the force are already perpendicular. So we can just multiply them out. The moment from the 100-pound force, so let's write that over here as moment due to the 100-pound force. That's going to be 100 pounds times 4 feet. It's going to be 400 foot-pounds. And since I'm going to assume counterclockwise moments are positive, this would be a counterclockwise moment, so it's going to be positive. So that one's easy because everything's at 90 degrees. The 150-pound force is not at 90 degrees. We need the perpendicular force. So I can draw this angle down here. This is my 30-degree angle. The perpendicular force would be the opposite side. So I've got a 150-pound hypotenuse. I need this opposite side. Opposite goes with sine. So the perpendicular component is going to be 150 pounds times the sine of 30. And if we go to the calculator, or you remember, sine of 30 is 1/2. This is 75 pounds. So the amount of this 150-pound force that is pulling this way, that's creating the clockwise moment, is 75 pounds. So we've got 75 pounds 2 feet away. The moment due to the 150-pound force, the perpendicular component, the component perpendicular to the arm, is 75 pounds times 2 feet. That'll give us 150 foot-pounds. It's clockwise, so this will pull here and produce a clockwise moment, so it would be negative. So negative 150 pounds for that one. And then the last one we've got is the 200-pound force, and we have to do the same thing. We've got 75 pounds measured, 75 degrees measured to the arm. We need the opposite side, and opposite side goes with sine. So this would be 200 sine 75 degrees. Now I don't have 75 degrees, the sine of 75 degrees in my head, but 200 times the sine of 75 is 193.18 or 19. So it's 193.19 pounds, and it's 1 foot away from our pivot point. So it's really down here. Even though we visualize it here as the right triangle, all the forces, the perpendicular and parallel components, all attach at the same point. We've got our perpendicular force here, we've got our parallel force there. So the moment due to the 200-pound force is going to be 193.19 pounds times 1 foot. So that's 193.19 foot-pounds. That would also cause a clockwise moment. Clockwise moments are negative. Now, according to the problem, it said to did it say anything about sig figs? Nope, no statement about sig figs. So we just treat it as a math problem and round it off to something reasonable, maybe 193.2. Everything else came out exact. So don't get thrown by it when it looks weird. Just remember the basic principles. Moment is perpendicular force times the arm. So find the perpendicular component, multiply that by the arm, the distance between the pivot point and the point of application, watch your signs, and everything will work out. Then the next thing we did was to find reactions at supports. And so we have a beam problem. And with the beam problem, we have to put moments together with our ability to resolve forces and draw a free body diagram. Now, something to watch out for in this problem is the supports are reversed from how we normally see them. Normally, we'd see a roller support on the right. Most of the example problems we did had a roller support on the right and a pinned support on the left, but this one is a little bit different. So don't be thrown by that. Just remember what you replace these things by in your free body diagram. So as I'll copy this over here, and then I'll switch over to the camera. 87 kips, B and A, and I'll copy the geometry as we need it. Looks like 10, 13, 14 feet. So there's the free body diagram minus the geometry. A was a roller support, and rollers only exert a force perpendicular to the surface they sit on. So this would be RA, and it would be RAY because it's in the Y direction. At B, we've got a pinned support, and pinned supports can react in two directions. We have RBY and RBX. Don't forget about RBX. We have a side load here. We have something at an angle, so there's definitely going to be something for RBX to work against. Now, the basic setup is to form our equations of equilibrium. Once we've got that free body diagram, we do our sum of forces in the x direction, sum of forces in the y direction, and sum of moments about a point. Well, sum of forces in the x direction, we don't pick anything up from RAY or the 45 kips force. We're going to pick up a piece of this 22 kips force, the horizontal piece or the adjacent piece to that angle. So that's going to be cosine. Adjacent goes with cosine. So 22 cosine 32 degrees. And it's to the left, so it'd be negative. Nothing from the 87, but all of that RBX. So that equation will pretty clearly give us our value for RBX. For the y direction, we'll have RAY up, so it's positive, down 45 kips, down the opposite side, that'd be the same as this length here, but applied at the same point of contact. So that's going to be 22 sine 32 degrees minus 87 plus r by. Now that one we can't solve right away because we don't have RAY and RBY. So we're going to have to rely on getting one of those from our moment equation. Now, as far as the moment equation goes, if we take our traditional pivot point around A, then nothing from RAY, nothing from RBX either, because the line of action of RBX goes right through A. We will pick up RBY, and RBY will have an arm of 14 feet, because this is, I think, it's 4 feet here, and then let's see what it was here. It's 3 feet there, 6 feet, 4 feet, and 1 foot. So we can get the geometry down there. That's a total of 14 feet. 6 and 4, 10, 13, 14. 14 RBY. Don't forget the arm in front of your unknown force. Most common mistake people make with this. They just have RBY in there, and they get some unreasonably large value for their force. It's because they don't really have the force, they have the moment. We need the arm in there so that we really get the force out. Now, RBY pushing up here would create a counterclockwise moment, so it'd be positive. 45 kips is at 3 feet, so we'd have 45 times 3 clockwise, so negative. We'd have the vertical piece. The horizontal piece of the 22 kips doesn't generate a moment. It goes right through the line of, right through the pivot point. So just the 22 kips sine 32 times the arm of 9 feet, also negative, clockwise. That'll be the moment for the 22 kip force. Then we've got this 87 kip force, 13 feet away, also clockwise, and nothing else. Now we crunch the numbers down, solve for RBY, substitute in RBY, solve for RAY. So the rest of it's just math at that point. Now, if we, this was about where we finished with our first exam. So the first exam covered an awful lot. Covered basic math, equilibrium problems, non-concurrent and concurrent problems, moment was all on there. Then we went into our second exam material, which was all about trusses. So our first problem here, we've got a truss, and we've got a mechanic who wants to hang a chain hoist from his garage roof and use it to lift 1,500 pounds. The roof truss is illustrated below. Determine the load in each structural member and complete the following table. So we've got a 4-member truss here, and it's kind of a modified, just typical roof structure. We've got this vertical piece here going up to the apex, and something that's only spanning 14 feet. We likely wouldn't bother with that, but that extra piece is there. So we've got a 4-member truss here, a 5-member truss. 1, 2, 3, 4, 5. Yep. 5-member truss. And the way it's set up, method of joints is about the easiest way to go. So to set this one up, the first thing we'd need is a free body diagram. And so we draw the free body diagram, the external problem. So we treat the structure as a single whole unit and find the reactions at the supports. So we've got an 8-foot height. We've got a 10-foot and a 4-foot span. We've got a roller at B, so that's RBY. We've got a pinned support at A, so we'd have RAX and RAY, and no other loads. So the picture is going to look something like that. So 1,500 pounds pulling down at this point. We've got our geometry. This is the same basic problem as what we just did in the previous one, finding the reactions at the supports. Sum of forces in the x direction equals RAX, positive. Don't forget your coordinate system, x, y, and counterclockwise moments. Well, RAX is the only force in the x direction. That's got to equal 0, so no RAX. Not there. Sum of forces in the y direction, we've got a positive RAY, we've got a negative 1,500 pounds, and we've got a positive RBY. Equal to 0, but we can't really do anything with it. Sum of moments, if we pick point A as our pivot point, we'll have 1,500 pounds 10 feet away, so that's 15,000 foot-pounds. Pinned at A, pulling down, would give us a clockwise moment. Clockwise moments are negative. Then we have RBY. RBY is 14 feet away. So we have 14 RBY. Pinned at A, pushing up, that would be a counterclockwise moment, so positive. And that equals 0. So we can solve for RBY, use that value to find RAY, and that would give us our supports. So let's see here. We'd have 15,000 divided by 14. Why did I pick such ugly numbers? RBY is 1,071.4 pounds. And that'll make RAY 428.57 pounds. So RAY 428.57 pounds. So those are our values for RAY and RBY. Now that's just the first step in the problem. We have to do method of joints here, which means we're going to have to do some analysis to figure out whether these members are in tension or in compression. And we have to have kind of a plan to march across the truss and pick up all the members. I would probably start at A. And to start at A, I'm going to need this angle here, which we can figure out from the triangle. I'd probably then jump to, I'd try to jump to D, but I might be concerned whether or not I have enough information there. So we'd have to look at it carefully. It looks like if I know member AD, then I'll have 2 unknowns there, so I'll be able to solve that. And it looks pretty easy to solve there because everything's at 90 degrees. And then jump to RB, and we'll only have 1 equation to solve. We'll still need the angle, but we'll be able to get the last member we need. So all 5 members will come out of method of joints. So let's set up how that'd work. Let's start with A. So let me see if I can put that off to the side so we can keep that free body diagram on there. So let's start with A. If we draw the free body diagram of joint A, I have RAY pushing up, and RAY was 428.57 pounds. We have, let's see, this was A, C, B, and D. So we have two other forces here. Remember, if you draw a little circle around there, whatever contacts or crosses through has got to be in our free body diagram. We have member AC, which I'm going to assume pushes down and to the left that way, which would mean member AD would have to do that. So this will be force due to member AD. This will be force due to member AC. I need my angle here, and sometimes it helps to sketch it out. It's getting a little messy over there. So I need that angle. That's my angle to horizontal. So it would be this angle here, and we can get it from inverse tangent of 8 feet over 10 feet. So we take 8 over 10 in the inverse tangent. We get 38.660. So 38.660. Yep, 38.660. Now that we've got our free body diagram, this is a concurrent force system, method of joints at A. So we do our sum of forces in the x direction. That'll be all of FAD to the right. And then a piece of FAC, it'll be the adjacent piece. So it's going to go with cosine of 38.660 degrees. And that'll have to equal 0. Sum of forces in the y direction will have positive 428.57 minus what's pulling down, which would be the opposite side. So it'll be FAC sine 38.660 degrees. And that'll equal 0. Now, the first equation we can't solve right away. The second one we can. If we rearrange this a little bit, and I'll leave the algebra to you, FAC would be 428.57 divided by the sine of 38.660 degrees, which comes out to be 428.57 sine of 38.660. That gives me 686.04. And that's pounds. Positive, so that means my assumed direction here is correct. And we'll come back to that in a moment. Now that we know member AC, we can go and figure it out for member AD. FAC times the cosine of 38.660 will tell us FAD comes out to be a positive 535.71 pounds. Also positive, so our assumed direction's correct. Now here's where it gets a little trickier. You have to interpret correctly tension versus compression. So you have to get back into that mindset. I know it's been a little while since we worked on this, but this is a good point to review tension versus compression. So the basic pictures, and something I would probably put on my index card if I was going to be taking this exam. If a member is in tension, then it's been stretched out. And a member in tension will tend to draw its supports back toward each other. Only something that's stretched out can exert a force on its supports pulling inward. So tension looks like this on a free body diagram when you're doing method of joints. When you're drawing the forces that the joint feels, it's opposite the force that the member would feel. Now, compression then would look the opposite way. Compression the member wants to stretch back out and it's forcing against its supports, trying to push them farther apart from each other. So that's compression. So let's look at what we've got for FAD. At joint A, member AD is to the right. So member AD is like that. Well, which picture does that one look like? Looks closer to tension. So member AD is in tension. 535.71 pounds of force in tension. Member AC is up and to the right. So it looks like that. That picture is closer to compression. It's pushing joint A away. So member AC is in compression. Now on the exam sheet, there's a table to fill out where you'd enter in the load. So member AC, we could key in member AC's load or write in member A's AC load. And they say 4 significant figures. So you'd round this to 4 sig figs. So 428.6 pounds, or sorry, 686.0 pounds would be what we'd fill in for AC, and we'd check the box for compression. For AD, we'd fill in 535.7 pounds and check the box for tension. Now I'll set up the free body diagram for joint D. Joint B is going to be very similar to joint A, so I won't bother with that one. But if we draw the free body diagram for joint D, just to review how we translate information in from members we already know, we've got our externally applied 1,500 pounds of force, and it would make a lot of sense to assume that member CD pulls in the opposite direction, so FCD. Now we know what's going on with member AD. According to our free body diagram and our solution here, member AD was 535.71 pounds in tension. And tension draws the endpoints together. So at A, that meant pulling to the right. At D, that's going to mean pulling to the left. The joints are trying to go toward each other in tension. So we know exactly what member AD is doing to joint D. It's pulling it to the left with 535.71 pounds of force. So it makes sense that member DB, member BD, if we stick to our alphabetical order, member BD has got to be doing the same. Well, now everything's at 90-degree angles here, so it's pretty easy to figure out the answers. FCD is 1,500 pounds, and FBD is 535.71 pounds. Member BD is over here, so member BD came out positive, so our direction's right. Member BD is pulling joint D to the right. That looks like this, so it's tension. Member CD is up here. Also looks like tension. It's pulling joint D upward. So both member CD and member BD are in tension. Then we can do the free body diagram at joint D. You'd have to figure out the angle, inverse tangent of 8/2. And you'd only need one of the two equations, sum of forces in the X or the Y direction. I'd probably use Y because it wouldn't bring anything in that I'd calculate. Because in the Y direction, all I'm going to have is RBY and a piece of FBC. Could figure out what that is pretty easily. So I think we'll finish that one there, unless there are any specific questions on it. So let's see here. So that was method of joints problem. Can probably guess what's coming next, a method of sections problem. And method of sections, we could handle some pretty ugly looking trusses without too much difficulty using method of sections. Because although there may be a lot of joints and a lot of members, we can jump right in the middle. We don't have to find method of joints walking across the truss. So let's take a look at the at the truss we've got. And there's scrap paper built into the exam, by the way. So here we've got a table to fill out. Only 3 members, so that's good indication that we're probably going to be able to take care of this in one section. Fill out the following table based on the structure below. Find the loads carried by the members and determine whether each member is in tension or compression. State your answers to 3 significant figures. And I've even given a hint here. Be very careful about picking the point about which to take moments. There is a choice that makes the problem easy. Essentially, that means if you pick a bad point, you're going to get more than one unknown in your moment equation, and that's never a good thing. We want one unknown. That's why I say here, if you feel like you're doing too much work to get your moment equation, or it ends up being complicated, as in 2 or more variables, you probably picked an inconvenient point. So let's take a look at the truss that we've got here. It's a typical roof truss. I forget which one this is, whether it's a Pratt or whether it's a Howe truss or something in between. But although it looks like a lot, it actually breaks down pretty well. We're looking for members BC, CI, and IJ. Well, BC, CI, and IJ are all in one line. We can cut right through them in one cut. We can even close. If we close to the left, all we'll bring in is our reaction force at A. Now, as you look at the problem, notice something about it. It's symmetric. It looks the same on both sides. And there's only one load right at the top, right in the middle. So you don't actually have to formally work out the reactions at the supports. You certainly could do your sum of forces in the x and the y direction, sum of moments about a point. Or you could just say, this thing's loaded in the middle. It's symmetric. Everything looks the same left to right. It makes perfect sense that this 19,200 pound load is going to be split evenly between A and G. So we don't really need to solve the external problem by going through the algebra and the analysis. We can just appeal to symmetry and say, well, if we've got 19,200 pounds and we split it evenly, 9,600 pounds is going to be at A, and 9,600 pounds will be at G. And that simplifies the problem a little bit. So it's really quick to get our external problem solved. Then we just need our internal problem. We need our section. And that's going to include, I'm going to close to the left on it. So I'm going to cut through BC. And that'll leave force FBC behind. I'm going to cut through CI, which will leave a force CI, and I'll cut through IJ, which will leave a force Fij. I've got 9,600 pounds at A. I've got each bay is 10 feet. So I'll label that 10 feet and 10 feet there if that comes in handy. And I'm also going to need an angle because member BC is at an angle. The easiest way to get an angle on this one is to use the big half truss here as a big triangle. You've got 30 feet going across the bottom, 20 feet up. So you can find the angle at A by doing the inverse tangent of 20 over 30. So we have 20 over 30 inverse tangent. That'll be 33.690 degrees. So 33.690 degrees. So let's jump to the free body diagram. That's what it looks like there. So I did my cut through right like this, and closed through A. I got my angle. I've got the 3 forces that I exposed. FBC, FCI, and Fij. Now notice something here. Although the problem looks really complex, we've got a really big advantage here. We've got FCI and FIJ at 90-degree angles to each other. That means the only thing that involves an angle here, and that angle would be to horizontal, would be the same 33.690 degrees, is going to be FBC. So let's start our equations here. Sum of forces in the x direction. We've got all of Fij, and then we're going to have a piece of FBC. It'll be the adjacent piece, so it'll go with cosine. So it'll be FBC cosine of 33.690 degrees. And that's all in the x direction. So not a bad x direction equation. Sum of forces in the y direction. We've got all of that 9,600 pounds up. We've got all of FCI up. And then we're going to have the opposite side of FBC. So that's going to go with sine of 33.690 degrees. Now, that's not a bad looking y direction equation, but neither of these can be solved right away because we don't have enough unknowns. We're going to have to rely on our moment equation. And here's where you can make or break the problem. It's all about where you pick your pivot point. If you try to pick your pivot point here at I, you have the advantage of knocking out FCI and FIJ, but you're going to have a pretty complex moment to find FBC because you've got to find the arm up here to FBC, or you're going to have to find an angle, and it's going to look really ugly and be problematic. It can be done, but you're going to have to be really careful about how you figure out your component and what the arm is and all of that. Or you could pick a different point. Well, we don't have too many other points left to pick. This point here is not looking great because you're going to get FCI and FBC in there, and you're going to have still a weird angle problem. You still have to find a cosine of FBC. But check out A. If we pick A as our pivot point, something kind of interesting happens. We lose Fij because Fij has a line of action going through A. So no moment there. We lose the 9,600 pounds because there's no moment there. We also lose FBC because the line of action of member BC goes right through A. So nothing from IJ, nothing from BC, nothing from the 9,600 pounds. The only force that'll show up in the moment equation is FCI. So A looks like a really good point to pick for our pivot point. Now the arm for FCI from A is 20 feet. So we have 20 FCI. It's even at 90 degrees, so no sines or cosines or anything like that. And there are no other forces trying to make a moment here. This would be a counterclockwise moment, so to be positive. There are no other forces trying to create moments. So that sum of moments must be zero. If 20 times something is zero, that something must be zero. FCI is zero. In this configuration, member CI is unloaded. Well, that produces a pretty good simplification here. We drop out FCI and we can solve for FBC. Once we know FBC, we can solve for Fij. Now, I'm not going to work through the rest of the algebra on that unless anyone really wants me to. But remember, interpretation of tension and compression is different in method of sections. In method of sections, by default, we assume everything is in tension. And if we get a negative result, it's in compression. So it's just easier to draw the free body diagram assuming tension. So that's the truss problem. Should be relatively fast to work out if you first see that you can use symmetry to solve your external problem, and then secondly, pick that correct point for pick the best point for your pivot. And it's a little bit different than points that we've figured out in the past. So a little bit different problem, but if you see that point, you should always go through and try everything, see if there's an advantage somewhere. But that's why I gave the hint that there is a point that makes the problem pretty easy to do. So that was the truss problem. And then everything else is kind of downhill from there. We went into our exam 3 material, which should be pretty fresh from last week. And we've got tension, compression, we've got stresses. Remember with stresses, the basic definitions. So your definition of normal stress and shear stress, of normal strain and elongation. I will give you any material constants you need. This is pretty similar to the first problem we had on our exam last week. You've got different members loaded up to 100 kips in tension. Determine the normal stress. Well, the equation is normal stress equals force over area. So really, this is a problem about calculating areas. So here you got a solid square rod with 2-inch long sides. So that's got to be a 2x2. That's 4 square inches. Hollow square rod. I saw some issues with these on the exam last week. It's a hollow square rod. Doesn't mean there's a hole in there, a circular hole. It means there's a square hole. So let's draw that one out here just to make sure it's clear. We've got this hollow square tube with 2-inch sides. So it's 2 inches across and 2 inches high, but it's set up to have 1/8 inch wall thickness, which is a pretty common piece of structural steel. We have 1/8 inch wall thickness. It's 0.125 inches. So let's go over to the screen here. To find the area here, you need the area of the shaded part. Well, the easiest way to do that is find the area from the outside. That's 2 inches times 2 inches. That's 4 square inches. And then subtract off the area on the inside. Well, to find the area on the inside, you need this distance right here. Well, that distance is 2 inches minus 1/8 and minus another 1/8. So it's 2 inches minus 1/4. So 1 3/4 inches, it'll be square, so it's the same dimension there. So you'd be subtracting off 1 3/4 squared, inch squared. So it's 2x2 minus 1.75 by 1.75, and that'll give you the area there. For circles, don't forget pi r squared had a number of small amounts of points missed when people use diameter instead of radius. If you're going to use pi r squared, you got to use an r. If you plug in a d, you're going to get 4 times the area, which is going to give you 4 times less stress. So basic definition, normal stress, force over area. And then we have shear stress. Shear stress uses the same equation. The area is different though. Shear stress is force divided by area, but it's the area resisting the load. And this question asks, we're going to use 12 1/8 inch diameter rivets. What's the stress if the load is 5 kips? Well, we'd need the area, the cross-sectional area of an 1/8 inch diameter rivet. And then we'd need the area of 12 of them. And we'd find that from our from pi r squared times 12, and then the 5 kips for our force. So that one would look something like this with the shear stress. The area of one rivet would be pi r squared. That'd be pi times 1/2 of an 1/8, which would be 1/16 squared. So we'd find that area. The total area is 12 times the area for that one rivet. The force is 5 kips. So our shear stress would be 5 kips divided by whatever the total area we found. And that would be some number of KSI. Not too many problems on that, short of area calculation issues for the most part. On the exam, people did pretty well with this. Just got to be sure you're finding your area correctly. Then we've got problem 9, which ended up being the last problem on this particular exam. And here we've got an elongation problem. So we have a stainless steel bar with 24 inches of length. Cross-sectional area is 57.6 square inches. So we have a bar that is 24 inches long. So a 2-foot long piece. The cross-sectional area, they don't tell us what the profile looks like, but they tell us the area is 57.6 square inches. So that would be what we'd see if we cut through the beam. It's loaded in tension with 12 kips of force. And the modulus of elasticity, they tell us, is 29,000 KSI. Now, the first problem they ask for the normal stress. So there's our drawing. Normal stress is force over area. We've got 12 kips over 57.6 square inches. So that'll give us some number in KSI. To find the strain is stress divided by the Young's modulus. So we'd take our stress, whatever that was from problem A, and divide it by 29,000 KSI. That would give us some small number, probably 0.00 something inches per inch. Then part C asks, what's the elongation? Well, elongation is the strain times the length. The strain tells us how much each inch grows. The length tells us how many inches we're dealing with. So we'd multiply the strain times 24. And that would give us our elongation. And then the last part is how much force would be required to shear through the bar if the shear strength of stainless steel is 60 KSI. So that would be the ultimate shear strength of stainless is 60 KSI. So the picture in this problem is we've got our bar and we want to apply a force to shear through it, to shear through that cross-sectional area. Well, the area is 57.6 square inches. That would be what would be exposed if we sheared through the bar. And what I had in mind here was shear that's used typically in welding shops. If you go over to the welding shop on the Utica campus, there is a shear, hydraulic shear, that you can put a piece of metal into. You push a foot pedal, and it comes down and it shears through that piece of metal. So you have different sizes that you can work with to weld up practice pieces, things like that. So that's what I was thinking of when I wrote up this problem. The shear stress, to get it to break, we have to hit the ultimate shear stress. So shear stress is force over area. We know the shear stress is 60 KSI. We don't know the force, but we do know the area, 57.6 square inches. So we'd cross multiply for every square inch. It's going to take 60 kips to shear through. We've got a heck of a lot of square inches. So we're going to end up with a really heavy load here. So you cross multiply that and you get some big number, somewhere around 360 or 3,600 KSI or kips, excuse me. So thousands and millions of pounds to shear through this thing, about 3.6 million pounds, somewhere in that neighborhood. So it's definitely a large amount of force that's going to take to shear through this. So that's a quick tour through the exam. At least that's the exam I gave back in 2017. Now, what we see Wednesday night could look similar, could be different, could have some other things on it. Look at our previous exams. It's not a bad idea. You got lots of resources to practice with here. Look at our previous exams and what we've covered on those. Look at the old exams that are online. Solutions to everything are everything except the final and the final are posted online right now. So I've got a practice final solutions. All the homework assignment and quiz solutions are up there. So lots and lots of resources to study from if you've got problem areas you need to practice with. Anyone have any questions?
No.
All right then. Well, if there's nothing specific, have a good night, and I'll see you on Wednesday.